Hi everyone, and welcome to another lesson on fundamentals of robotics. I'm Dr. Maddie Babayasol from Mechatronicks, and I'm more than honored to be your instructor today with another lesson on foundations necessary to express robot motion. This lesson has also a written version in our website. My suggestion is to watch the video first and then go read the reading for a deeper understanding. Also, be sure to watch other lessons on fundamentals of robot motions, because some of the lessons are prerequisites for this lesson. In the previous lesson, we became familiarized with rotation matrices. And we saw that the 9-dimensional space of rotation matrices, subject to 6 constraints, can be used to implicitly represent the 3-dimensional space of orientations. There are also methods to express orientation with a minimum number of parameters, which is 3 in 3-dimensional space. Exponential coordinates, the 3-parameter Euler angles, the 3-parameter roll-PGI angles, the Cayley-Rodriguez parameters, and the unit quaternions are some of the methods to express orientations with fewer number of parameters. In this lesson, we will focus on one of the ways to explicitly represent the space of orientations that we call exponential representation. To learn more about the explicit and implicit representations of configuration, please refer to the lesson on configuration and configuration space. Exponential coordinates of orientation are a 3-parameter representation of orientation in which a rotation matrix R can be parameterized in terms of a rotation axis omega hat. The hat notation shows that the vector is a unit vector, and an angle of rotation theta about that axis. If we combine these two parameters, we get the exponential coordinate representation of orientation as the product of omega hat and theta. If we write omega hat and theta individually, we get the axis angle representation of rotation. There are 3 interpretations for the exponential coordinate representation omega hat theta for a rotation matrix R. The first interpretation for the exponential coordinate representation omega theta for a rotation matrix R is the axis omega and the angle theta, such that if a frame was initially coincident with the space frame S, were rotated by theta about omega, then its final orientation with respect to S can be represented by R. The second interpretation for the exponential coordinate representation for a rotation matrix is, if we consider omega hat theta as an angular velocity expressed in S frame, such that if a frame was initially coincident with the space frame and followed omega hat theta for 1 unit of time, then the final orientation is expressed by R. In other words, if it's integrated over this time interval, the final orientation will be expressed by R. The third interpretation is, if we consider omega hat to be the angular velocity expressed in the space frame, such that if a frame was initially coincident with the space frame, followed omega hat for theta units of time, then the final orientation can be expressed by R. In other words, omega hat is integrated over this time interval to get the final orientation as R. The exponential coordinate representation of orientation got its name because of the link to the linear differential equations. We'll see this link in the coming slides, but let's first learn some notes about the linear differential equations theory. From mathematics, we recall that the scalar linear differential equation has the form x dot t equal to axt, where xt belongs to R, a is a constant, and the initial condition is x naught. Then the solution of this scalar linear differential equation is straightforward and can be found as xt equal to the exponential function e to the power of at times the initial condition. The series expansion of the exponential function can be defined as the series. The scalar case can be generalized to the vector linear differential equations case in the form of x dot t equal to axt, where xt belongs to Rn and A is an m by n matrix, which is constant, and the initial condition is x naught. Then, similar to the scalar case, the solution can be expressed as xt equal to the matrix exponential e to the power of at times the initial condition. The series expansion of the matrix exponential can be found similarly to the series. Now the question is, what are the conditions that this series converge? The answer can be found in most textbooks on ordinary differential equations, and we bring that up here without proof. If A is constant and finite, then the series is always guaranteed to converge to a finite limit. With this reminder about the linear differential equations, let's get back to the exponential coordinate representation of orientation. Exponential coordinate representation of orientation can be viewed or used in two ways. It can be viewed as a unit axis of rotation omega hat, with a rotation angle theta about that axis. This representation is called the axis angle representation, and it's very useful when representing a robot joint, where we can separate the joint axis from the motion theta about the axis. Or it can be viewed as the 3 vector omega hat theta in R3. Now let's see the analogy between the exponential coordinate representation of orientation and the linear differential equation. Suppose that a 3 vector P starts from the initial position P naught and rotates about the rotation axis omega hat by angle theta and reaches the position P theta. Note the circular path that the vector is traveling. Also, assume that all quantities are expressed in the fixed frame coordinates. This motion can be visualized as this demonstration. Rotating the vector from the initial location P naught at time t equal to 0 to the new location P theta at time t equal to theta results in the rate theta dot to be 1 radians per second. Remember that rate is a numerical value, whereas velocity has a direction. From the physics of the circular motion, we know that the tip of the vector pt traces a circular path during rotation. And we also know that the velocity of pt is tangent to the path and can be calculated by the cross product of the angular velocity and the radius vector of the circular path. Remember that the velocity has a direction, whereas the speed is a numerical quantity. So the speed can simply be the product of the radius and the rate of the angular velocity. The velocity of the tip of the vector is calculated as p dot equal to omega times r. The angular velocity omega can can simply be calculated as the rate of the angular velocity, in this case it's 1, in the axis of rotation direction. Omega is omega hat times theta dot, and our theta dot is 1, so our angular velocity is equal to the axis of rotation. And from the geometry, we can write that Q plus R equal to P, and thus the radius is equal to P minus Q. Therefore, the velocity of the circular path can be found as P dot equal to omega hat cross product with P. The cross product of omega hat and Q is 0, since the angle between them is 0. So the physical meaning of this velocity can be visualized in your salad spinner in your kitchen. If you spin the wedgies in the spinner, they would go through circular motion. And as you can see, each water droplet also goes through this circular motion, and the velocity is tangent to the circular path. So as you can see, the water droplets jump out of the basket and they're collected here. As a quick reminder that if A and B are two vectors in R3 defined by their coordinates as A equal to A1, A2, A3, and B equal to B1, B2, B3, and the angle between the two vectors is theta, then the cross product of the two vectors can be defined in two ways. It can be calculated by the product of the magnitudes of the two vectors and the sign of the angle between them in the direction of the unit vector perpendicular to the plane containing A and B in a right-handed coordinate frame, or it can be calculated by the formal determinant as this. Remember that the cross product of B and A is in the opposite direction of the cross product between A and B. Now let's go back to the analogy between the exponential coordinates of orientation and the linear differential equations. Using the skew-symmetric representation, we can change the equation for the tangent velocity described in the previous slides to a linear differential equation of the form P dot equal to bracket omega hat P with P naught as initial condition, where the bracket omega hat is the skew-symmetric matrix representation of the vector omega hat. By definition, if we have a vector defined as A equal to A1, A2, A3 in R3, then the 3 by 3 skew-symmetric matrix representation of A can be defined as bracket A and with this formula. Note that since bracket A is a skew-symmetric matrix, then the transpose of bracket A is equal to minus bracket A. The solution to our linear differential equation, as we saw before, can be expressed as Pt equal to e to the power of bracket omega Tp naught. And since t and theta are interchangeable here, we can write that P theta is equal to e to the power of bracket omega theta times P naught. From this equation, we can see that the matrix exponential is a transformation that rotates the initial vector about an axis to the final position, and thus it's the rotation matrix R. You can see the different applications of a rotation matrix in the previous lesson. Now let's see if we can find a closed form solution for this matrix exponential. From the series expansion that we saw before, we can write e to the power of a bracket omega hat as this formula. This equation was derived with the help of the following equations and also the series expansions for sine and cosine. The above formula for the matrix exponential is called Rodriguez's formula for rotations. and it uses the matrix exponential to construct a rotation matrix from a rotation axis omega hat and an angle theta. Formally, we can define this as, given a vector omega hat theta in R3, in which theta is any scalar and omega hat is a unit vector, then the matrix exponential of bracket omega hat theta in little SO3 can be calculated using the Rodriguez's formula. This is the same formula we saw in the previous lesson when we talked about the general formula for the rotation operators. It actually takes the 3×3 little SO3 representation of exponential coordinates and calculates R in big SO3 that is achieved by rotating about omega hat by theta from an initial orientation R equal to the identity matrix. Therefore, we can say that the matrix exponential above can act as an operator and rotate a frame or a vector. So, pre-multiplying a vector by this rotation operator can rotate the vector about the fixed axis omega hat by an angle theta. Also, if R is a rotation matrix with 3 column vectors, then pre-multiplying R by this rotation operator is the orientation achieved by rotating R by theta about the axis omega hat in the fixed frame, and post-multiplying R by this rotation operator is the orientation achieved by rotating R by theta about the axis omega in the body frame. If you don't know what the body frame or the fixed frame is, please refer to the previous lesson on rotation matrices. The matrix exponential takes the skew-symmetric representation of exponential coordinates omega hat theta and calculates the corresponding rotation matrix. The set of all 3×3 real skew-symmetric matrices is called little SO3, which is called the Lie algebra of the Lie group big SO3. In general, the space of n by n skew-symmetric matrices is called SON. For any rotation matrix R in big SO3, we can always find the unit vector omega hat and a scalar theta such that R is equal to the matrix exponential e to the power bracket omega hat theta. This brings up a new discussion about the matrix logarithm of rotations. The matrix logarithm is the inverse of the matrix exponentiation discussed in the previous slide. In fact, the matrix exponentiation integrates the matrix representation of an angular velocity bracket omega hat theta in little SO3 for 1 second to give an orientation R in big SO3. On the other hand, matrix logarithm differentiates an R in big SO3 to find the matrix representation of a constant angular velocity bracket omega hat theta in little SO3, which, if integrated for 1 second, could rotate a frame from the identity to the matrix R. So now the problem is, if we have the rotation matrix R in big SO3 as R defined as its column vectors, what are the corresponding omega hat and theta? In order to find these, we need to equate the matrix exponential formula to the given rotation matrix, where S theta is the sine of theta and C theta is the cosine of theta. By subtracting the transpose of each matrix from both sides, we can get these equations. As long as theta is not an integer multiple of pi, that is, sine theta is not equal to 0, we can write the above equations as these equations. Expressing these equations in skew-symmetric matrix form, we can get bracket omega hat as this equation. Omega hat gives the axis of rotation for the given r. Bracket omega hat is not well defined if theta is an integer multiple of pi. And those angles are called the singularities of the representation. As we saw in the configuration and configuration space lesson, singularities are unavoidable for any three-parameter representation of orientation. Euler angles and rolled PGI angles have the same singularities. Now assume that sine theta is not equal to 0, and we want to find an expression for theta. We equate the known rotation matrix R to the matrix exponential from Rodriguez's formula. By taking the trace of both sides, we can get the expression for theta as this equation. Remember that the trace of a matrix is the sum of diagonal terms. For any theta satisfying this equation such that theta is not an integer multiple of pi and bracket omega hat defined in the previous slide, R can be expressed as the exponential matrix e to the power of bracket omega hat theta. Now let's discuss the case where theta is an integer multiple of pi. If k is an even integer, then no matter what the axis of rotation omega hat is, we have rotated back to the initial orientation, r equal to I, so the vector omega hat is undefined. If k is an odd integer, then trace of r is equal to -1. And r can be calculated using the Rodriguez formula as I plus 2 bracket omega hat squared. Expanding this expression for r, we get this equation. And thus, the diagonal terms and the off-diagonal terms can be written as these equations. Please note that R is a symmetric matrix since R transpose equal to R. These equations are used to find the solution for omega hat, and once such a solution is found, then we can say that R is equal to the matrix exponential e to the power of bracket omega hat theta, where theta is an odd integer multiple of pi. So in summary, if we are given R in big SO3, using the approach discussed, we can find the theta and a unit rotation axis omega hat such that e to the power of bracket omega hat theta is equal to the given R. The vector omega hat theta is the exponential coordinate of R, and the symmetric matrix bracket omega hat theta in little SO3 is the matrix logarithm of R. Since every R in SO3 satisfies one of the conditions, for every R there exists a matrix logarithm bracket omega hat theta, and therefore a set of exponential coordinates omega hat theta. Remember that if omega hat is a solution, so is minus omega hat. As an example, if the rotation matrix R is defined by successive rotations about the z-axis of the space frame by 180 degrees, followed by a rotation about the x-axis of the space frame by 90 degrees, we want to find the unit vector omega hat and an angle theta such that R is equal to some e to the power of bracket omega hat theta. From the expression that we found for R, we can see that trace of R is equal to -1. So using the equation to find the angle of rotation, we can find that the angle of rotation is equal to 180 degrees. So we are dealing with case 2, that by checking the two conditions that we discussed, we can find that the axis of rotation can be either of these vectors. Remember that if omega hat is a solution, so is minus omega hat. Then we can say that the orientation of the frame achieved by a rotation from the initial orientation about omega hat that we calculated here by an angle 180 degrees gives the same orientation as the frame if it was rotated first about the z-axis of the space frame by 180 degrees, followed by a rotation about the x-axis of the space frame by 90 degrees. If you want to visualize this rotation, watch the short demonstration that follows. Okay, I want to show you these two consecutive rotations and the final orientation that we got. Suppose that we have this frame X, Y, and Z, which is at time 0 coincident with our space frame. Now we want to rotate this frame by 180 degrees about the z-axis of the space frame or the base frame. This is the base frame now. So I want to do 180 degrees rotation about the z-axis. Now this is our current frame. The second rotation is about the x-axis of the fixed frame again in this direction, and we would do 90 degrees about the x-axis of the fixed frame. So the final orientation would be like this. As a demonstration, consider a 2 degrees of freedom robot wrist mechanism in 0 position depicted in this figure. 0 position means that all joint angles are set to 0. So initially, theta 1 and theta 2 are set to 0. If you're not familiar with the degrees of freedom for a robot, you can check the lesson named Everything About the Degrees of Freedom of a Robot first. From this figure, we can see that the axis of rotation of the first joint is 0, 0, 1, which is the z-axis. And the axis of rotation of the second joint can be easily calculated as omega hat for joint 2. Thus, the orientation of the gripper can simply be calculated by the product of matrix exponentials and then expanding the matrix exponential using Rodriguez's formula and inserting the values for the axis of rotation. Now that we find the gripper's orientation, the question is there any set of angles theta 1 and theta 2 so that in those positions the orientation given by R can be achieved? In other words, can this mechanism reach to this orientation? To answer this question, if we take the third row of the product of matrix exponentials and then set it equal to the third row of the given orientation, we can see that there is no theta 2 that satisfies this equation, and thus we can conclude that the wrist mechanism cannot reach this orientation. That's going to wrap up today's lesson. I hope you enjoyed it and now have a good grasp of the exponential coordinates concept. Be sure to send us your feedback or any questions that you have. In the next lesson, we will learn about other explicit representations of orientation. See you in the next lesson. Bye.